for velocity. In special relativity, coordinates between different inertial frames are transformed via the Lorentz transformation. In this context, the velocity takes different values depending on the observer, inertial frame, and therefore does not constitute a Lorentz invariant quantity. That is, a quantity that takes the same value in every inertial frame. We therefore introduce the concept of the velocity, whose components transform under the Lorentz transformation in the same way as coordinates. The velocity itself is not an invariant, but its magnitude, self-inner product, remains constant at the square of the speed of light in every inertial frame, which allows us to maintain consistency in relativistic discussions. Up to this point, we have obtained the relation between the line element representing four-dimensional distance and proper time. ds² equals minus cd tau squared. These are invariants since ds² equals minus c dt squared plus dx² plus dy² plus dz². The following holds as an invariant. We now divide both sides by d tau squared, the proper time, which serves as a universal clock. Recall that dx_mu equals dx0, dx1, dx2, dx3 equals c dt dx dy dz. Therefore, dx_mu over d tau equals dx0 over d tau dx1 over d tau dx2 over d tau dx3 over d tau is defined as the relativistic velocity u_mu, a quantity with dimensions of velocity obtained by dividing the invariant four-dimensional distance by the invariant proper time. To explore the physical meaning of the velocity, let us write out its components. Using d tau equals 1 over gamma dt, this becomes This shows the calculation process of expressing the velocity in terms of the coordinate components, so please pause and work through it at your own pace. In the non-relativistic limit, v much less than c gamma is approximately equal to 1, so the spatial components reduce to the familiar Newtonian velocities. Note that even when v equals 0, particle at rest, the velocity does not vanish. Normalization of the velocity. We derive the equation known as the normalization condition of the velocity. In this video, we use this equation as the foundation to derive relativistic energy. We define the velocity from ds² equals minus cd tau squared. Since ds² equals eta mu nu, dx mu dx nu, it follows that dividing both sides by d tau squared and using u_mu equals dx mu over d tau. This is called the normalization condition of the velocity. Let us examine the physical meaning of the normalization condition of the velocity. We write out all the components. The key point here is that the individual components of the normalization condition of the velocity are not independent. They are interrelated, and together they combine to give the square of the speed of light, which is a constant. While the velocity itself is not an invariant, the normalization condition of the velocity is a Lorentz invariant, a physical quantity in special relativity whose value does not change under Lorentz transformations, taking the same value for all observers, and therefore indispensable for describing the universality of physical laws. Let us verify this. We start with the Lorentz transformation of the coordinate differential dx². From here, the calculation steps are displayed, so please pause and work through them at your own pace. We have thus proven that the four-velocity transforms according to the Lorentz transformation rules. This confirms that the normalization condition yields the same value minus c² in all inertial frames. Let us examine the physical meaning of this result. We begin by looking at the magnitude of the velocity. Let us express the non-zero components using the combination of the Minkowski metric and the four-velocity in this equation. Here, we multiply both sides by -1. The Minkowski metric changes sign by definition, so there is no problem in doing this. We will start from this form for convenience. The calculation steps are displayed here. Please pause and proceed at your own pace. This expression shows that the magnitude of the four-velocity of any object in Minkowski spacetime, c d t dx dy dz, is always c. Now let us focus on the squared form of this expression. The time component, u0, u0, and the spatial components, u1, u1 plus u2, u2 plus u3, u3, are not independent. They are interrelated, always maintaining the constant value c². This is what we mean by the distribution between the time and spatial components. Looking at γ² c² minus v², we can see that gamma corrects the distribution between the time and spatial components while maintaining the constant value c². This expression is a Lorentz invariant. It holds in every inertial frame. Every entity in the universe distributes its velocity between the time direction and spatial directions, yet the magnitude of its four-velocity is always c, the ultimate speed limit of this universe. Next, let us consider the perspective of proper time. Think of it like a VR game, where movement in the spatial directions is 0. Let us recall when we introduced the concept of proper time. Even though one is aware of moving in the spatial directions, from one's own perspective, one remains at the origin O of Minkowski spacetime. This is the normalization condition of the four-velocity from a subjective point of view. You are using all of your speed c solely in the time direction, moving into the future. In fact, it is precisely when you are at rest in space that you move through the time direction at the maximum speed c. The faster you move through space, the less speed remains for the time direction, and the slower time passes. In any observer's proper time frame, you are at rest and moving only in the time direction at the speed of light. When you observe other entities from an objective point of view, they are also moving in the spatial directions, and part of their speed is distributed to the spatial directions. slowing their progress in the time direction. This is the true nature of time dilation. Of course, the same can be said when someone observes you. However, from either perspective, the invariant quantity is c². No special inertial frame exists. The distribution of speed between space and time may vary, yet the total is always c for every entity at every moment. You, the Earth, the galaxies, and everything with mass in this universe are moving through space-time at the speed of light, even at this very moment. The passage of time itself is the proof. For if any portion of that speed were not directed into the time direction, time would not flow. 4. Momentum. In Newtonian mechanics, momentum is given by P equals mv. In special relativity, we extend this concept to four-dimensional spacetime and define it as the form momentum as follows. Let us first look at the spatial components. When the velocity is sufficiently small compared to the speed of light, gamma is approximately 1, and this reduces to the momentum in Newtonian mechanics. E equals mc². Let us examine the time component of the form momentum, and from it derive the equation that revolutionized our understanding of the world upon its discovery by Einstein, E equals mc². We begin with the normalization condition of the form velocity, multiplying both sides by the square of the mass m, since the form momentum is defined as p mu equals mu mu. This equation is also a Lorentz invariant. Although the components of the momentum vary depending on the frame, the equation takes the same form in every frame. Let us substitute each component. Taking the square root of both sides, the time component is p0 equals gamma mc, which has the dimensions of momentum. Multiplying this by the speed of light c gives a quantity with the dimensions of energy. Let us define Cp0 as the relativistic energy E and examine its physical meaning. The intermediate calculation steps for deriving the relativistic energy are displayed here. Please pause and proceed at your own pace. Here, let us confirm that the expression inside the square root reduces to gamma. We have derived the relativistic energy E equals gamma mc². What does this equation tell us physically? Let us find out. Let us start with the energy of a system at rest. With V equals 0 and gamma equals 1, we have where E0 denotes the rest energy. This tells us that even a stationary object possesses energy, and that mass and energy can be converted into one another. This energy is extraordinarily large. The square of the speed of light is approximately 9 times 10 to the 16th. Even a tiny mass holds an enormous amount of energy. Just 1 gram contains energy equivalent to the atomic bomb dropped on Hiroshima. Let us look at this in the context of everyday velocities. We expand the Lorentz factor gamma using a Taylor expansion. To clarify the meaning of the equation, we bring mc² inside the parentheses. This represents the total energy of a moving object as observed from a rest frame. The first term is the energy of the object at rest, the rest energy that appears for the first time in relativity. The second term is precisely the kinetic energy of Newtonian mechanics. By extending momentum to four-dimensional spacetime, the existence of an enormous amount of energy that humanity could never have known before Einstein has been revealed.